Hello, and welcome to Palisade Corporation's webcast, Applied and Efficient Modeling in Natural Resources, Case Studies of Mining and Oil and Gas, presented by Kurt Reinhardt and Francisco Zagmut of EPIX Analytics. My name is Jameson Romeo Hall, and I will be your host today, and I'll be available to help answer technical questions by chat. At this time, all attendees are in a listen-only mode. Please note that as an attendee, you're a part of a larger audience today. The attendee list is suppressed to maintain attendee privacy. We will be holding a Q&A session at the conclusion of today's presentation. You may ask an online question anytime throughout the presentation today by clicking on the Q&A panel. I would also encourage you to visit our website and sign up for a free trial download of our software, including our lead products, At Risk, and the Decision Tool Suite. We invite you to sit back and relax and enjoy today's presentation. Currently, Francisco has the presentation.
Perfect. Thank you very much, Jameson. Hello, everyone. My name is Francisco Zagmut. I'm a managing partner at EPIX Analytics. We are risk analysis and decision analysis consultancy, and we wanted to share today, together with Dr. Reinhardt, a couple of case studies based on our actual work on mining and oil. So the idea of this talk, I guess I'll go to the next slide, and I'll describe this a little bit. But before I get there, maybe Kurt, would you like to say hello to everyone?
Sure. Good morning, everyone. My name is Kurt Reinhardt, and again, as Francisco said, I'm one of the risk consultants working at EPIX Analytics and doing risk and optimization work largely. Thank you.
Perfect. Thank you very much, Kurt. So let's go to the next slide. We first wanted to discuss a little bit why we build models, and this question is really a question for decision analysis as opposed to pure modeling sciences. So in our world, we build models to support decisions, and because of that, what we have to deal with frequently, especially in our client work, is to deal with what is available in terms of data and knowledge. So unlike pure scientific work where one has the chance of saying, I wish I had this data to come up with a decision, when we are supporting decisions at a corporate level, especially in an environment like natural resources, we have to deal with what we have. We cannot have a wish list of data. Therefore, a key aspect of successfully building a model that informs a decision is to be able to make assumptions and simplifications while still trying to strike a balance between insightful answers and manageable data-driven models. So how can we do that? How can we strike that balance between having a model that is driven by data and is simple enough so it can be used and is manageable? So the purpose and contents of this talk will focus on the idea then that based on some of our consulting projects, and in this case we're going to talk about two case studies, we will discuss how we manage to reduce complexity and use what I call in quotes tricks, mathematical tricks, to make decision supporting models that make that balance between being sound, providing useful answers, and yet being simple enough so they could be data driven and easy to understand. So Kurt will go through the first case study. That is an interesting case that we had in oil and gas optimization modeling, and then I will describe a mining forecasting model that we worked on. And before we get into the actual details, I wanted to mention that you will see throughout the slides certain numbers in blue. I'm pointing with my cursor here. This number M and 4 digits is basically a reference to a free risk analysis tool that you can find in our website. It's called Model Assist for At Risk, and basically it's a collection of different methods and risk analysis, quote-unquote, tricks that we have learned throughout our years of experience in doing consulting, training, and research in risk analysis. So keep an eye on this during the webinar, because once you're done, you might have some technical questions that we were not able to address during the time of this talk, but you can actually find them simply by going to this hyperlink, and then once you get to Model Assist, which which you can either install or visit online, you can search for these terms. Okay? So I will hand it over to Dr. Reinhardt here. Kurt, I will make you the presenter so you can drive this directly, okay?
All right. And there we go. Let me get in presentation mode. Are you able to see that? Is that going, Francisco?
Looks good. Yeah.
Okay. So again, good morning. I'm Kurt Reinhardt, and this situation that we'll present here is one about portfolio optimization, and specifically it was about a portfolio of drilling programs for a large oil and gas company. And when we got the call, they had been working on this problem already, and so they said, look, we already have this large stochastic optimization model, but it only gives us an answer after it runs for 3 days. And even then, we know, based on other information and multiple runs of things, that we're not necessarily getting to the optimal solution. And so they were looking for some help with this. And of course, you can imagine with a large problem and stochasticity, variation and uncertainty in there, it can be difficult. And so, hold on. There we go. And so, again, their objective here was to optimize their drilling programs across a large number of different wells in different areas. And so specifically the decision was to select a set of wells to drill. And now they had substantial uncertainty about costs and many other factors that went into determining the ups and downsides of each of the opportunities that they had. And so, but ultimately they're looking to maximize their oil production from drilling, subject to the standard set of constraints of, they had restriction on their budget, they had limitations on equipment just in terms of availability of suitability for specific tasks, location relative to the geographic distribution of wells and things. They had limitations on labor that was available. And there was also access constraints. Some of the sites were only accessible in the winter. And so all of these things contributed to the complexity of the problem that they needed to try and really cut through in order to get the insight that they needed. And so they had developed a problem to a model to address this problem that took advantage of optimization such as you can find in the risk optimizer and at risk. And so what risk optimizer helps you do is it basically takes a Monte Carlo model that deals with the risks around a certain project, and then it layers an optimization on top of that. So essentially when you run risk optimizer, you run it on a Monte Carlo model that you've developed. Excuse me. And so when you run the optimizer, it'll run the full Monte Carlo model for all the iterations that you have. And then it will check to see if your optimization constraints have been met. Am I still under budget? Does this meet my constraints on equipment and such? And then risk optimizer checks to see if the objective, your maximized production or revenues or whatever it may be, to see if that represents an improvement over the previous iteration. And if it does, then the machine will save that result. It will reshuffle your decision variables, and then it will repeat this process. And you can manage the settings for this either as the number of trials that you go through or the amount of time that the algorithms spend looking for the solution. But you can see that you might run the risk optimizer for 1,000 trials, but each one of those trials includes the complete run of your Monte Carlo model. So you're taking all the complexity of the Monte Carlo and growing it almost exponentially. You're growing it very quickly in terms of being able to run through these alternate scenarios. And so really the problem is this. And this is a quick view of the Colorado Rockies out our back door, so to speak. And these mountains represent, this terrain represents the solution space to an optimization problem. It expands in many dimensions, And what you're looking for is the highest part in there. But in your journey to find that highest point, you're going up many slopes and down many slopes, and there's just this huge terrain that you would have to search. And so it's difficult to efficiently find your way around in there, and that's one of the things that contributes to very slow and suboptimal solutions for a stochastic optimization problem. And so what I want to talk about with this case study are some elements of model design and implementation that improve Monte Carlo runs and also are going to improve the ability to use them in an optimization setting. So the first problem is how many possible solutions do you have? You know, if you're optimizing a portfolio of 25 projects and you can accept or reject each of those 25, there's actually 33.5 million different portfolios that you could choose from. And if you have 50 projects, that's going to be over 1 quadrillion projects. At 200, and our client had nearly 400 individual wells they were looking at. If you have 200 projects, then there's this many different potential portfolios, and I don't know if anybody even knows the name of that number, but there's probably no need to. So clearly, as the size of the candidate options, the available options grow, the complexity grows, and this just represents the vast increase in that space you have to search. So what can be done about this? Well, there are a number of different things that we can try. A good place to start is to see what you can do to speed up the Monte Carlo simulations. So in the analogy of that landscape, you want to see if you can spend as little time as possible evaluating any individual piece of ground. You know, you want to be able to get to that point to see if it's a high point or a low point and then move on quickly. And so that's the advantage of speeding up your Monte Carlo simulations, and that'll get you through all those optimization cycles more quickly. Another thing you can do is to try and constrict the decision space a little bit. If you're looking for the highest peak in Colorado, you can write off the whole eastern half of the state that's all the prairies. So that's a whole area that maybe isn't eliminated by the constraints of your decision, but it's clear that the combination of factors in that area is never going to contribute to an optimal decision. And so sometimes we can identify those situations ahead of time and limit the space that needs to be searched for the optimal decision. And then we can also take a look at how we discretize the solution space, how we're going to chunk up the information. And the analogy here is if you have to go out and measure elevation on every square foot of Colorado to find the highest peak, you're never going to get the job done. But if you can measure the elevation on a per acre basis or a square mile, you've now changed the resolution of the landscape in a way that it's reduced the burden of making that search. And so in this case for our client, what we were able to do is we were able to work on the first and the third elements here to speed up the Monte Carlos, and then also to take a look at how that solution space was put together. And in terms of speeding up the Monte Carlo simulations, what we were able to do is take advantage of the central limit theorem, which many of us were introduced to in college and promptly forgot. But in our work along these lines, we've really found opportunities where we can take advantage of what might seem like this very abstract concept, but is actually a very powerful tool that you can take advantage of. So in this case, what we're talking about is for a large N being a sample size. So for a large sample, the mean across that sample, and we'll call that mean X bar. X bar, the mean of N independent, identically distributed variables, will be distributed according to a normal distribution with the mean of mu and a standard deviation of sigma divided by the square root of the sample size. And now the mu and the sigma in this formula, those are the mean and the standard deviation of the original distribution, the distribution that we're drawing these N samples from. So we have samples coming from a distribution with a mean of mu and a standard deviation of sigma, if you want to simulate the mean of that, you could simulate 100 individual samples and then calculate the mean, and that's what you would return from your Monte Carlo. Or you could just simulate the mean directly and dispense with all the individual draws of that sample, because we can just use this mathematical relationship in order to simulate from the distribution of the mean of those variables. And there's another part to the central limit theorem that and this is the one that we were able to use in this particular case, and it deals not with the average but with the sum of those independent, identically distributed variables. So the sum of those variables, the expected value, is going to be the sample size times the average, and that will be distributed according to the individual average times the sample size, n times mu. And the standard deviation will be the square root of n times sigma. So again, we're using the parameters from the original distribution, and we're applying the sample size to it to model a different distribution. And so now what we wanted to get were aggregate summed values, and so we were able to take advantage of this to simulate those sums directly, and that reduced a lot of the overhead in the simulation. So let me just show a couple examples using at-risk just to demonstrate the central limit theorem. In this case, we're looking, say, at drilling costs, and drilling costs are distributed as log normal with a mu of $1.5 million, say, and a sigma of 0.1. And now this red histogram, this is the distribution of the mean, x bar, of 19 individual wells. I simulated the drilling costs for 19 wells and took their average, and that's what we built this distribution on. And so the mean of this distribution is 1.5. So it's mu. It's the same as the original distribution, just as the central limit theorem suggests. And the standard deviation of the average is 0.024. And 0.024, if we actually do the calculation as suggested by the central limit theorem, we can see that sigma from the original distribution divided by the square root of n, so that would be 0.1 divided by the square root of 19. That is 0.024. So the value here that we're told in our at-risk output matches the actual calculation that we're able to do. So just a quick demonstration of the central limit theorem. It's not just a concept. It actually works. And then here we do a similar example using the sums. And again, this is what we did here. It's the same distribution for drilling costs. The blue histogram is simulating 5 individual wells and taking the sum of the cost. And the red distribution, that's almost perfectly hidden there because they match so well, this is just simulating from the central limit theorem distribution of the sum of those variables. And so we can see that the parameters of these two distributions match very well. The means are exactly the same, and the standard deviations are, within tolerance, exactly the same as well. We would clearly get there if we increase the number of iterations here a little bit. So again, in the case of averages and sums, as long as the components are coming from the same distribution, we can use the central limit theorem to simplify the calculations. And so what I have here are just a couple of toy examples that reflect what we were able to implement for this client. And so, I do want to continue. So what we have here is an example of portfolio optimization. And we have all of our individual wells listed down here. And in this case, I just have 25, I believe. And each one has a distribution from which we can sample the costs and a distribution from which we sample the revenues. And what we're trying to do here is we want to maximize the total revenue, the sum of this column, subject to the constraint that the total costs are going to be less than our maximum budget. And so the first step is that one that I mentioned before about discretizing, or how you want to bundle up your information. So it's true in this case we have 25 individual wells, but it's also true that these wells share some characteristics in recognizable groups. They're located near one another. They can be serviced by equipment. You wouldn't necessarily drive and drill this well and then drive away without doing that one and that sort of thing. So there are some aspects of the problem itself in the details that suggested these natural groupings. The other piece of the puzzle that made these natural groupings is because of the similarities with these wells, we're using the same distribution to simulate the costs and the revenues here. So the first step here is, rather than make decisions about each individual well, what I did is I grouped them together into projects or programs, and I have 4 of them here. So this is the first group in this box. This is the second group. And now you can see that this is my decision as to whether or not I'm going to drill this well. But this variable is tied to here, so my decision isn't based on these 25 separate decisions. It's just based on 4 decision variables here, because if I choose to execute program 1, I'm going to drill all of those wells. And so already we've been able to reduce the number of potential variables. We've simplified and reduced that landscape that has to be searched for the optimization. And so we calculate our costs and our revenues, and if the program's not selected, then of course it contributes nothing to either one. And so this is a very simple example, clearly, that we set up, and we can run the risk optimizer very quickly. Let me just change this a little bit, get something to do here. And let me just run this briefly. And for those, some folks may have or may not have used this risk optimizer, but already this line here is just showing me my progress in the optimization. And if it can find a better objective, this line will jump up. This is the total revenues right here. So we run this, and of course this problem is so simple. It's actually, there's one better solution that it'll take a few minutes to get to, but this is the essence of running one of these simulations, and what it's doing is a Monte Carlo, and then it's checking to see if the objective has been improved, and then it's reshuffling and reshuffling. I'm going to stop this here just so we don't waste our time doing it. But and then we end up with this solution. This was the best solution on average that the engine was able to find. And so we simplified the problem in this case by lumping together a lot of the individual variables. Now I want to go to the next piece here where I can, let me just get this one. And here's where we really take advantage of the central limit theorem. So this is essentially the same problem, but you can see how it's been greatly condensed. Now, I'm still operating on the program basis. My decision variables are whether or not I select those individual programs. But instead of simulating each well independently, now I'm going to use the central limit theorem, and I'm going to just simulate their sum directly. So again, I'm using the individual mean times the number of samples for the mean. And the standard deviation is the individual standard deviation times the square root of n. And so this distribution here is the distribution of the costs of 5 wells altogether. And so now we've been able to simplify the decision variable side by lumping everything together, and we further simplified it by reducing the overhead on the Monte Carlo simulations by simulating just these 4 values instead of simulating 25 values that we then boil down. And so we would do a similar process here of risk optimizer, and I could hit start. And it runs, you know, the thing, if we really wanted to test this out, of course, again, this is a very simple problem, but we could zero all of these out. We run our optimizer, and then it ends up returning exactly the same solution as we find with the larger model. We don't see a big difference here with these simple ones, but obviously in a more complex case with 400 wells that you could maybe boil down to 75 different programs or something like that, then you can reduce a tremendous amount of the space that needs to be searched and the complexity of that space that needs to be searched as well. So let me just go back to the PowerPoint here. So structurally, by being able to impose those, we were able to improve on the product that this company had already developed to meet their specific technical needs. Now, the trick is that this company, as with most people who are engaged in this work, they're not looking to run a model one time and then stick it in the closet and pull it out again a year from now. People are engaged in these problems. They really want to understand the problem as well as understand what the solution is. And so by providing faster, more efficient solutions, you can provide better decision support because it opens up the feasibility of being able to run these models multiple times to look at different scenarios and to really play with them in a constructive way for the users and the decision makers. And then it also simplifies the model, and a simpler model is one that's going to be easier to understand by the users and the decision makers, which in turn makes their output easier to understand and easier to accept. So again, in this case, we were able to restructure the decision space a little by grouping things together. We were also able to take advantage of the central limit theorem in order to simplify the Monte Carlos that went into the optimization routine. So that's the end of the first case study here. So I'm going to hand this off to, Francisco. How do I?
There we are.
Okay, I guess I'm done. Thanks.
Thank you very much, gentlemen. Kurt, thanks for going through that case study. So now we talked about a real business problem, and as Kurt mentioned already, this was a real case, a real consultancy that resulted in a real model for a very, very large oil and gas company. And it did make a practical difference. So what we wanted to point out again is it's not just about the science, which is what Kurt showed, the central limit theory and its applications, but also how that science can be put to work to the benefit of an applied problem, in this case is a client of ours. So the other case we wanted to discuss has kind of the same idea here. We wanted to first talk about the problem, and then I will show you one of the several tricks that we had to use for that particular problem. So these concern forecasting the production of a mine, and evidently having a reliable short and mid-term forecast is very crucial for planning and budgeting. In this case was for a large open pit copper mine. The client really needed help improving the accuracy of production forecasts because in the past they have had a hard time trying to find numbers that were consistently close enough to be able to do proper planning and budgeting. But the problem was that the production of a mine, of course, depends on lots of variables. So they were having a hard time trying to figure out which variables were key here. This is just an example, by the way, of a forecast over time of production. These numbers are not real, just to maintain a confidentiality for this client. But the idea was to be able to provide a forecast that will provide not only just what we expect, which is that dotted line here in the middle, the mean production, but also confidence bands. So this, in this case, the difference between the 97.5th and the 2.5% confidence will be what we call the 95% confidence interval. So what variables affect production in a mine? Well, first and foremost, if you talk with any mine engineer, they will say it's the geology. So is there stuff? and once we know if there is stuff, of course we have to create a mine plan, which is a very complex kind of model and geological work to be able to say where are we going to be digging and how much, so where to get it. And finally, there is weather, which is very important as well. Can we get the stuff? So for example, if you have a very rainy season, you can have a situation where there's a lot of mud. Evidently, that picture was not taken from a mine, but this picture was. And what happens is that sometimes you have problems digging. The equipment may get stuck. In this case, it's a large excavator that got stuck. So these are kind of environmental plus geology issues, but also we have equipment things that can affect production. So how can we get it? And you see here, I have a picture on the top right of a large power shovel. And at the bottom, you see it's one of the trucks that are used, that are loaded by the shovel to transport material into what we call the crusher, which is where the rocks are crushed to then go into what we call the mill, which is where the mineral is extracted. So if you were wondering, by the way, who those guys are, if you wanted to see my face, you can zoom in, and that's me. So these are very, very large machines, and there are multiple machines moving around the mine, moving material, and so on. And of course, we have the other issues like staff and contracts. So will we have staff and people that will get the stuff we need as planned, and will others, say all the contracting around the mine, will be able to help us? So that's just a list of some things, just to point out the complexity that comes into what is produced in a mine. And in general, not just for this mine problem, but in general, one principle that we try to stick to in our work is to always start simple, at least at the beginning. So if you are, for example, a mine engineer, and say you took some modeling training, evidently when you have learned new skills and you understand a system very well, you want to model reality, right? You start modeling and want to be very realistic. Now, realistic doesn't always mean insightful. And why would that be? Well, there's several reasons for that. First and foremost, the more realistic your model is, the more parameters it will require. And if you need more parameters, you will need more data. Data that many times we don't have available. It's also linked to data that it will be harder to update. So you heard Kurt's talk before when he mentioned that this particular client will be running this model very often during the planning season. This was also the case for this model, that it had to be run monthly, for monthly forecast, yearly, and every 3-year forecast as well. And of course, there is the issue of transparency. The more complex a model is, the more we compromise transparency. This is not really a linear relationship, so this symbol equal here is a bit misleading, but sometimes a very complex model will be very hard to tease out. In other words, even though it may be very realistic and may be intuitive for, say, a mine engineer or anyone associated with the mining industry, it may be very hard to understand what is the impact of every input in the model, how do those inputs affect my outputs. And of course, there is the issue of making mistakes and speed, which may or may not be important in the speed, but mistakes evidently are very important. So again, the key is to start the model as simple as possible and then add complexity as needed, as opposed to thinking of the ideal model and then trying to trim out the complexity. Why do we say this? Because from an efficiency perspective, from a budgetary perspective, it's always a good idea to start something that could be manageable in the shortest time possible. So for this project, again, the complexity came from many sources. As I said before, all the variables above, weather, geology, staff, machinery, etc., were key to quantify production. None of them were irrelevant. So for example, geology and mine plan, the plan dictate extraction, and the mill capacity constrains extraction. Trucks and shovels required to extract and transport rocks are very key, of course, because If they are not working, then we won't be able to transport the material. So therefore, looking at that big picture, the initial suggestion from this client was for us to basically model the entire mine dynamics. That is, include the geology and mine plans, model how that interacted with all the machinery, for example, the trucks and the shovels, and also how those machines will interact with the crusher. Again, is a machine that basically crushes the rocks into smaller pieces, and then the mill, which is where we process all the material to get the mineral. So this could indeed be done, but is it needed? Well, if you think about how to do this, of course, there will be a large amount of data and a large budget that will be required to do this. And the question that as a decision analyst, as a risk analyst, one has to ask is, would it make a real difference? So how do we simplify this complex problem? Despite intuition, despite all that we discovered before, by looking at the historical records, and luckily this particular client has very good records on pretty much all aspects of the mine, we established that geology was really not that important for the uncertainty in the forecast. And I would like to highlight the word uncertainty here. In other words, in order to predict the future, geology was very important to know how much we were going to get on average. But for the uncertainty on that how much, so how big or how little, the geology wasn't that important because the mine engineers already knew it and they had a plan for it. So what was really important to understand the variations in the future, what we don't know is going to happen, was the unplanned time that the machines were down. In other words, when things were broken. And specifically, when you think about a mine, you have these very large shovels, and there's only a finite number of shovels. So if, for example, 2 shovels are down, you will have a big drop in production. So the model then relied in known inputs, for example, the geology, the mine plans, and, for example, the plant maintenance of machines. But we also modeled the unknowns using a probabilistic model together with empirical relationships. In other words, we said, rather than trying to figure out all the dynamics of the mine, let's use the historical records, which are very detailed, to figure out relationships between the different key variables. And this came down to many different modeling methods, but a key aspect was to have robust regression models to figure out the relationship, for example, here between the time that the trucks were ready and the tonnage that will be produced. Again, this is distorted from the real data we had from the client to protect confidentiality, but you can see here, for example, that these are dots for different shovels in this case, and some shovels had more production than others, even after taking into account the time of the trucks that service that shovel. So let's go to a specific technical challenge. I mentioned before that this model relied largely, or in part actually, in regression models. And since we were using regression models to understand the uncertainty, in this case, in the time that the machine would be down, we had to figure out a way to connect this uncertainty to our at-risk or to a spreadsheet model. So in reality, it is very hard to create complex, robust regression models in Excel, at least to estimate the parameters for them. Now, in contrast, we do need to have the parameters and the data in the same place, because that's where the model will reside, especially if you're using at-risk. So a key thing about regression parameters is that the slope and the intercept are negatively correlated. So just a refresher on regression, here I have a very simple example where I have my predictor variable, or what is sometimes called the independent variable, and on the vertical axis I have my outcome that I'm trying to predict, which is my dependent variable, y. And basically we have observations, which is each one of these points, and we fit a straight line. This is the simplest form of a regression model. And when you fit a straight line, what we try to figure out is these 2 parameters. The blue parameter is the intercept, which is the place where that line crosses the vertical axis. And then the yellow parameter is the slope, which is simply the inclination of this line. So evidently, if the slope goes up, the intercept has to go down, and therefore, if the slope goes down, like in this case, the intercept has to go up. Which means that if we're modeling not just the point estimates of these two parameters, but their uncertainty, in other words, the distribution of what would be the real value of these two parameters, then we need to take into account that correlation. So there are several options. In fact, the easiest option to use in at risk would be to use the rank order correlation, which is built into at risk. However, that rank order correlation really assumes that the relationship is completely linear, which is a limitation of that methodology. Now, another option, of course, would be to just say, look, we're going to use the stat software outside and then bring the results into Excel and sample from them somehow, keeping that correlation. So there are ways to do this. For example, the risk resample function in at risk provides a way to resample in order, so we can sample all these parameters basically side to side. However, that's very clunky, if I can use that word, very slow, and if you wanted to connect directly to stat software, you will have to program that connection, and it's more work than you will expect for this kind of application. Now, another option then is to use one of the many hidden gems in Excel. I don't know if many of you have seen this function. It's called linest, and there's also an alternative called logest, which actually allows you to estimate fairly complex multiple regression models with more than just one predictor, and not just linear relationships, but also nonlinear relationships. I won't have time to go through the details of this function, but I will encourage you to look into it. And again, there are multiple references here that you can visit in Model Assist to understand more how this works. Now, what I want to say is that once you estimate your parameters, then to know the uncertainty in them, we have a couple of options. One is to use resampling methods, commonly called the bootstrap, which is a very good and reliable method, but it is slow, and it requires quite a bit of size in your spreadsheet. And I will show you an example in a minute on how will that work. And then there is another trick, which is called centering. The idea of centering is basically adjust the data to get rid of the correlation between these two parameters. So how do we do that? If we start with my regression model as before, what we have is, again, a slope and an intercept. So if we were to subtract the mean from each observation, what we would do would be effectively to shift the entire line towards the mean of the independent variable. So you see what happens here now is that the slope remains the same, but now the intercept has been pivoted to the middle of that line. So whether the slope is up or down, the intercept should be more or less the same number. So that is a very, very easy way of dealing with this correlation between the intercept and the slope. And luckily, if you are working with a multiple linear regression model, the first assumption that we make is that if we have more predictors, say we have multiple independent variables, they are by definition uncorrelated. So we wouldn't have to deal with correlation between multiple slopes, just slopes versus the intercept. So now that we do this, once we convert the data, basically we can fit our model in Excel. And again, there's a reference here on how to do that. And we can then simply assume that the intercept and the slopes and certain distributions are uncorrelated. So let's quickly look at this model. And what I have here basically is, again, this is a toy example where we have data. This is my predictor and this is my outcome, which is plotted here on the right. This is the same line that you saw earlier on my slide. And what I did here was to basically subtract from each one of these observations. I did this number minus the mean of all the x values, and that centered the line. So that is what I have here on the left. I simply subtracted from each one of my observations on the left, I subtracted from the mean of the values. Okay? So once I have this center data, all I really need to do is in Excel to now estimate those parameters. So an option to estimate the parameters, especially if we're talking about just one predictor, will be to use the Excel function slope, where I just specify my data sources. And then I can also use the intercept function. And finally, to get the error, in other words, the deviations from the line that are not explained by my line, then I can use this function called STEYX. That's all nice and great, but again, if we had multiple predictors, we couldn't do that. So there is another function, which I mentioned earlier, called the line_s function, that allows you to basically do the same, but it's an array function. So you see here, I'm using these curly brackets because I'm saying all these cells here are linked together. So we're estimating the parameters, which I mapped for you in different colors, so you see how this is equal to that, and this is equal to that. But we also can estimate not just one-on-one, but multiple predictors. Okay? So you can see here that what I have in this table here is my original estimates, just as they are here, and then the center ones, in other words, using not anymore my original data, but my center data. And what I'm getting from my line_s function here is the standard error of each one of these estimates. In other words, if I wanted to look at my uncertainty now, which is what I have on the right, on each one of these parameters, I can simply say that the uncertainty is a normal distribution where the mean is equal to my estimate. So for example, the slope would be 3.39, that's the mean. And the standard deviation is the standard error of that estimate. So the uncertainty, so the true value of that parameter will look like this. And then we do the same for the other parameters, for the intercept. Now, by doing that, we're basically saying, you see, these things are not connected, so we're not modeling any correlation between them. Because we centered them, so we said, because I shift the pivot point here, I can reasonably assume that there won't be any correlation. Now, if we use the bootstrap, what we're trying to do here is to say, look, I'm going to take samples of pairs here. In other words, I'm going to say I take a random sample, in this case of the 7th observation, which is here, for x and y. So that's what I'm reporting here. And then I take another sample of the 9th, and so on. So you see, if I take a few random samples, you'll see what the bootstrap does is to preserve the correlation between the two variables, and then I simply estimate the parameters based on the bootstrap data, not on the original data. So the bootstrap, basically, rather than getting rid of the correlation as I did with the center estimate, I simply say I will estimate my parameters with a built-in correlation. Okay? So if I was to run this model, let's actually run this model and see what happens. What I have here is the prediction of each value. In other words, I will say, well, what if I observe an x that is equal to, say, 25? I can plug that into my equation and come up with a prediction of what will that future value be. So what I have here is basically incorrectly modeling the uncertainty in the parameters without centering, in other words, assuming that they are uncorrelated, even though they are. Then I have the same prediction using the bootstrap where I'm taking into account the correlation. And then I have my centered prediction where I got rid of the correlation so I can take random samples without worrying about that correlation anymore. So let's run this model. And you see what we have here is that the bootstrap, let me maximize this so you can see it better. The bootstrap and the centering method look very, very close. So I'm going to switch now to my slides because I have this exact figure highlighted. So you see the 95% confidence interval is very close. There is a slight difference. Again, part of it is due to chance, and part of it is that when centering, we are saying there is no correlation. There is a tiny bit of correlation that we're ignoring, but it's not a practical difference in the correlation. Whereas for the correct method, when we actually didn't take into account or didn't reduce the correlation somehow using centering, we have much wider confidence intervals. So although in this figure it doesn't look that strikingly different, we're talking now, say, in billions of dollars, a difference between 99 and $105 billion is a big, big difference. And more importantly for this model, of course, it made it much more efficient to run and very simple to implement and update because everything lived in Excel and it didn't require having to create a bootstrap for every correlation and every relationship we had in the model. So, as conclusions for this talk, we wanted to say that in general, problems modeling, decision, and risk analytics are very complex. So I say often, but perhaps it's always complex. And the modeler has to find a balance between complexity and usefulness, especially considering data available and the decisions to be informed. Therefore, before embarking in a complex model, we should always think about simpler options that may be sufficient to inform a decision, and also consider perhaps not structural simplicity, but ways, using mathematical ways to reduce the complexity of the model while still keeping the same principle. And Kurt showed you a very good way of doing that using the central limit theorem, where we reduce the size of a model by several folds. And I also show you how using the centering also help us reduce the complexity of the actual implementation of the model. So there are many of these methods, and of course the question is where do we get these methods? One option which we have been showing you here is model assist. Again, we provided a link here for you, but there are many other places to learn these methods. A good starting point is, of course, the statistical literature, but also there are good modeling books that will describe some of these tricks. So we would like to thank you for your time. Both Kurt and I will be happy to answer any questions that you have if you want to email us or speak with us. Our emails are in there. And also, if you want a free copy of the models, just feel free to email us or our colleagues at Palisade, and we'll be happy to share these example models with you.
Well, thank you.
Very much.
Yeah, thank you, Kurt and Francisco. I think I do have a question here. One of our attendees would like to see slide number 19 again.
No problem. There we are.
Let's see if we have a... Perhaps that was it. We'll just leave that up for a minute. Good, and let's see if we have any other questions.
Well, while we're waiting, I'd like to just make one comment about this slide. And again, the point that Francisco is making is it's very valuable because a lot of people, when they start with a modeling project, they're concerned first and foremost with the realism of their model often. And how can I represent all of the complexities and all of the rich structure in this problem that I confront in my job every day or something like that. And starting simple is sometimes just a practical necessity, but it also helps get you, we believe, to a place of having a better, more efficient model in a very quick way. And so often a good way to start is to just sit down at your computer and build the quickest, simplest version, the most ridiculously simple version of your problem that you can, just so you get this bare prototype up on a spreadsheet. And then that'll help you think about it in a lot of interesting ways, and it will save you a lot of time building in complexities that then later you may just have to go in there and cut out. Well,
good. Can you explain a little more about one of the bullet points that says complexity equals.
Francisco, you want to take that?
Sure. I was answering in music. Sorry. So basically, as I mentioned before, the equal sign is a bit strong. But what I try to say with this is that if it was the bigger the complexity, the more transparency, it will be an equal without the inverse. But 1 over transparency, what I try to say there is that the more complex a model is, the less transparent will be for the decision maker. Okay. So that less transparency is not really linear in the sense that sometimes a very complex model can actually be easy to understand for a decision maker because it's very realistic. But from a point of view of trying to tease out what input variables are important in the model, then it becomes very complicated. However, we do have good tools, for example, in at-risk that help us understand that using, for example, the sensitivity analysis.
Oh, how to limit the number of parameters? Where is the limit? The complexity or the relations correlations?
That's a very good question. Unfortunately, there is no easy answer to that in terms of saying, look, it's an equation, because it really depends on the linearity and non-linearity of the relationships. Of course, the minimum number of parameters is 1, and the maximum is infinite. I would say in our practice, what we try to do is to find the least number of parameters that will give us an answer comparable to a more complex model. If you are talking specifically about, for example, fitting distributions to a model, there are very intuitive ways of doing this now. In fact, at-risk since version 6.0, I believe, has a way of testing this using information criteria. For example, when you try to fit a univariate distribution to parameters, you will have the ranks, the different distributions rank by an information criteria, like a Kaike information criteria or Bayesian information criteria. Those specific methods allow you to basically say, look, the fit is as good that I will pick the first fit because it has less parameters than the second. So they basically penalize by increased complexity in a fit. That methodology can be extended to simulation models, but it's a bit harder because in order to do that, you have to have a likelihood function, which is not always available in a complex simulation model.
Thank you. And that answered. Thank you. That was the report back. I think we have time for one more question. And then, of course, if you have any more questions, you can forward them to me, and I'll forward them to our team at Epics. Let's see. We'll wait another. I think things were very clear to everybody, so we really appreciate that. That's good news.
All right.
Well, if we get more later, and if you're watching this recording sometime in the future, please reach out to us. We'll be glad to hear from you.
Thank you very much, Jason.
Yes.
I wanted to thank you for the opportunity of sharing some of our case studies with you guys. And once again, both Kurt and I will be happy to answer any questions, and our emails are in there. Feel free to send us a direct email or through Palisade so we can continue this dialogue.
Yes. And
absolutely. Thank you very much.
And thank you, everybody.